Relevance logic, often called relevant logic, is a family of non-classical logical systems designed to capture a notion of implication and inference in which the premises are genuinely relevant to the conclusion. Roughly speaking, relevance logicians aim to block inferences where the conclusion follows from the premises purely for structural or formal reasons, rather than because of a meaningful connection between them. The central idea is simple but radical. A valid implication should involve some shared content between antecedent and consequent, or at least some informational connection. Relevance logic therefore revises classical logic's account of implication, while often retaining much of its familiar propositional structure. Classical logic validates several principles that have struck philosophers as counterintuitive. For example, in classical logic, any false statement implies any statement whatsoever, and any true statement is implied by any statement. Thus, from New York is in Australia, one can validly infer the sea is sweet, and if grass is purple, then Paris is in France, is classically true. Many have argued that such implications fail to capture how reasoning actually works. They seem to violate the intuitive idea that premises should matter to conclusions. Relevance logic is motivated by the desire to preserve a tighter connection between implication, explanation, reasoning, and our pre-theoretical intuitions, especially in philosophical, mathematical, and computational contexts. The most significant difference between relevance logic and classical logic lies in the treatment of implication and structural rules. Classical logic validates structural principles such as weakening, adding irrelevant premises, and explosion, deriving anything from a contradiction. Most relevance logics reject at least some of these. As a result, not every logically true conditional of classical logic is valid in relevance logic. Contradictions need not trivialize a theory. Valid arguments must preserve relevance between premises and conclusions. Despite these differences, relevance logic often retains classical truth, functional connectives such as conjunction and disjunction, though their interaction with implication may differ. The syntax of relevance logic typically resembles that of propositional logic. One starts with a set of propositional variables and builds formulas using connectives such as negation, conjunction, disjunction, and implication. The crucial difference is not the surface syntax but the rules governing implication. Some systems also include additional connectives such as a fusion or intentional conjunction, which plays a key role in expressing relevance formally. Several semantic frameworks exist for relevance logic. One influential approach uses possible world semantics, often extended to include non-normal or impossible worlds. These worlds allow us to model inconsistent or incomplete information without collapse into triviality. In this setting, formulas are evaluated relative to worlds, but the truth conditions for implications are not the same as in standard modal logic, where if-then sentences often are treated as strict implications. Instead, relevance logics often employ a ternary accessibility relation R, W, U, V. Intuitively, U and V together provide relevant information for evaluating implications at W. Using the ternary relation, the truth condition for a conditional A implies B at a world W can be stated informally as A implies B is true at W if and only if for all worlds U, V whenever R, W, U, V holds, and A is true at U, then B is true at V. Some add the following condition: if W is normal, R, W, X, Y if and only if X is identical to Y. So if W is a normal world, A implies B is true at W if and only if for all worlds X if A is true at X, then B is true at X. This structure allows implication to depend on how information flows from antecedent to consequent. By imposing different constraints on R, we obtain different relevance logical systems. Within relevance logic, a sentence is often said to be logically true if and only if it is true at all normal worlds in all models of the system, and logically false if and only if false at all such worlds. A sentence is logically contingent if and only if it is true at some normal worlds and false at others. Logical consequence is defined semantically. A conclusion, C, follows from premises S, if and only if, in every model and every normal world whenever all members of S are true at that world, so is C. Validity of arguments is defined accordingly, but with the important caveat that relevance constraints prevent many classically valid but irrelevant inferences. Relevance logics admit a variety of proof systems, including sequent calculi with restricted structural rules, natural deduction systems with relevance-preserving constraints, Hilbert-style axiomatizations, display calculi and labeled deductive systems, and semantic tableau systems. Each proof method highlights different aspects of relevance, such as resource sensitivity or informational flow. Stronger relevance logics can be obtained by adding constraints to the ternary relation R. These correspond to stronger principles governing implication and conjunction. By carefully tuning these constraints, logicians can construct a spectrum of systems ranging from very weak relevance logics to systems approaching classical logic. Relevance logic can be combined with predicate logic, modal logic, temporal logic, deontic logic, epistemic and doxastic logic, etc. Such combinations are especially useful in computer science, philosophy, linguistics, and theories of information, where relevance and context sensitivity play central roles. Many relevance logical systems enjoy important metalogical properties, such as soundness and completeness with respect to their intended semantics. Some systems also satisfy decidability or have well-behaved proof-theoretic properties, though these results often depend on the strength of the system. Several famous relevant logics are undecidable. Relevance logic represents a sustained attempt to align formal logic more closely with intuitive and philosophical notions of implication and inference. By rejecting irrelevant entailments while preserving rigorous formal structure, it offers a rich alternative to classical logic, one that continues to inspire work across logic, mathematics, philosophy, and theoretical computer science.